Sorry, the video cut off on the end of the tail, or the tail end of the last one. And as I was saying, a circle is just a one of the types of ellipses. Okay, so ellipses come in various families, and a circle is a specific type of ellipse where the two foci, right? So the two foci. Hang on, let me get my pen here. Okay, I've got my pen back. Where the two foci here lie right on top of one another. Okay, so a circle is nothing more than when the two foci lie right at the same point. Okay, now of course that's not a great circle, but you get the idea. All right, so there's one more thing that we want to mention about ellipses before we actually dive into Kepler's laws, and that is their ovalness, or their ellipticalness, is measured with a number called the eccentricity, which is given by E. Okay, so E stands for the eccentricity. And the eccentricity is just a measure of how non-circular the ellipse is. And eccentricities run from values of 0 to 1. Okay, so a perfect circle has an eccentricity of 0. Okay, and that means that the foci lie right on top of one another at the center of the ellipse. Okay, so an eccentricity of 0 would be a perfect circle. Right, now an eccentricity of 1 is essentially a straight horizontal line, right, where the ellipse has been so flattened out that it is essentially a straight line, and the foci lie along the ends. Okay, and you have everything in between 0 and 1, which will produce a closed ellipse. Okay, now that begs the question: what are typical planetary orbit ellipses, or eccentricities rather? And the answer is actually, surprisingly, even though our orbits are not perfect circles, they're fairly close. Okay, if I were to show you a picture of the shape of Earth's orbit, your eye would by far not be able to detect that it wasn't a perfect circle. Okay, you actually have to get fairly eccentric, up to about 0.2 or 0.25, a quarter of eccentricity, if you will, before you actually can detect that it's not a perfect circle. Right? So planetary orbits, for example, okay, Earth's eccentricity is 0.0147, right? Much closer to the 0 than the 1, indicating it's a very nearly a perfect circle. Okay. So now, what does all this have to do with Kepler's laws? So let's go through these one by one, and let's redraw our ellipse, or an ellipse rather, and this will just represent the orbit of any planet. Okay, so if we come back up here to Kepler's laws, if we come to Kepler's laws, all orbits are ellipses with the sun at one focus. So Kepler's first law says if I have a planet orbiting around the sun, then the orbit will describe an ellipse, and the sun will be at one of the foci, or one focus. And that begs the question, what's at the other focus, right? What's at the other focus? And the answer is nothing. There doesn't have to be anything at the other focus, okay? There doesn't have to be anything at the other focus. The answer is nothing, or empty space, okay? So the other focus is just a geometrical point in space, all right? It's just a geometric point in space. But we have our planet, and we have the sun, right? So we have the planet, and once again, if I slice this orbit down the middle this way, and then again this way, okay, so this distance A here is what's known again as the semi-major axis. That's going to be important. Now, what about Kepler's second law? Okay, So this is the first law. The planet is going to stay on this ellipse, and the sun is at one focus. Okay, that's the first law. The second law, all orbits sweep out equal areas in equal times. Okay, so this is usually the most difficult of the laws to grasp conceptually, but it's really not that bad. Okay, so I'm going to redraw the ellipse so as not to get so busy. All right, and hopefully this will make more sense. And I'm going to put two foci down. And what this law is saying, okay, all orbits sweep out equal areas in equal times. This was a revolutionary law because when we were dealing with perfect circles in the Ptolemaic system, and even in the Copernican, the first rendition of the Copernican heliocentric system, everything moved on perfect circles. And so it stood to reason, if everything was moving on a perfect circle, then its speed ought to be uniform. So this was a fundamental teaching of early astronomy, that all planetary bodies, their speeds must be uniform through space, right? If the heavens are perfect, then everything must move in an unchanging manner. Okay, that was the basic reasoning, right? What Kepler's second law says, it's not that the motion of objects are constant, but there is something constant. And that thing, to a professional physicist, we would call it orbital angular momentum. Okay? But to the layperson or the student, what is the same are these areas. So what do we mean when we say area? Okay? So imagine, if you will, we have the sun. And we have our planet out here, right? And it's orbiting this way. So eventually, it's going to maybe get here, okay? And the farthest point that it can possibly get, we call that aphelion, all right? And as it's near aphelion, it's going to be moving very, very slowly, comparatively, right? Because it's farthest away from the sun. So it's not going to be moving as fast out in this region as it would when it's closer to the sun up here. Right? And so what Kepler's second law says is the speed isn't constant. It will slow down and then speed up as it's moving around, but the rate at which its angle changes, or the area of the angle that it sweeps out, is constant per a given unit of time. So what that means is, let's suppose that we track our planet for 1 month. Okay, so we track our planet for 1 month, starting here, and we track it until it reaches here. So 1 month later, it's here. And remember, it's moving slowly out here. So if I look at the planet up here, maybe I look at the planet when it's starting right here, and I track it for a month, and it will maybe do something like this. It'll be all the way over here, right? And so what this law is saying is, if I draw the pizza slice from the sun to the two respective starting and ending points, then I have this area right here, right? This area right here. And remember, this was over the course of 1 month. If I do the same thing with up here, then I sweep out this area, this pizza slice, if you will, right? And what Kepler's second law is saying is these two shaded regions, the red region and the green region, are equal. Even though the green region has a small angle, it has a large distance, or a large leg, right? So this leg is very long comparatively, even if this angle is not very large. Whereas the red has a very large angle, but not very long legs, right? And so what the effect is, these two exactly cancel out, such that the area swept out from the sun, as measured from the sun, is going to be equal, okay? So what about the third law, okay? What about the third law? So once again, let's draw our ellipse. And we have two foci, and the sun is right here. And remember, Here's my semi-major axis. Here's A. Okay? So that's my semi-major axis. Kepler's third law says this. The orbital period P, the square of that, is equal to the cube of the semi-major axis. Now, what is the orbital period? The orbital period is the total time it takes to complete one orbit. So if my planet is here and it's orbiting around the sun this way, then the period is just the time it takes to complete one full orbit, right? It's the time it takes to complete one full orbit. What Kepler's third law is saying is that the period squared must equal the semi-major axis cubed. Now, you may be wondering, how can I have a unit of time equal to a unit of distance? That doesn't make much sense. And in fact, there is a proportionality constant here. I'll call it K, if I can draw one. And this K actually has, in our units, okay, in the units that Kepler would use, has the value of 1. So we typically just ignore it. Now here's why. Okay, for Kepler, P is going to be measured in years. And A is going to be measured in astronomical units. Now, 1 astronomical unit is the average distance Earth spends away from the sun. Okay, and again, our orbit is very, very circular, and so our average distance does not change very much. It's very slight. Okay, the change is very, very, very slight. And so what that means is, if I, on average, am 1 astronomical unit away from the sun, and it takes 1 year to orbit the sun, then 1 year squared does indeed equal 1 year cubed. Okay, or 1 astronomical unit cubed. 1 squared is 1, 1 cubed is 1. But there is a slightly more, I hesitate to use the word complex, but it is slightly more complex. There's a slightly more complex way to write, and by the way, that equation, P cubed, or P squared equals A cubed, does not just hold for the Earth around the sun, even though those are where we derive our units from. The Kepler derived his units from. It does hold for every single planet. So if I measure any planet in the solar system, if I measure their orbital period in years, and I measure their semi-major axis in astronomical units, then this equation will hold. P squared equals 1 times A cubed. Okay. But if I use different sets of units, and we talked about different sets of units a little bit. We talked about kilograms, we talked about meters, and we talked about time, okay, being in seconds. And if I do that, then Kepler's third law in more general units, okay, in SI units essentially, would take this form. Okay, P squared is equal to 4 pi squared A cubed over Newton's gravitational constant times the sum of the masses. Okay, and Newton actually derived this version. Okay, Newton actually derived this version. Now, why is this significant? Okay, because it turns out in units of astronomical units and years that G is equal to 4 pi squared. Even though we gave it the value of 6.67 times 10 to the negative 11 the other day, that's its units in SI. If I convert those lengths and times into astronomical units and years, then G actually equals 4 pi squared. So 4 pi squared over 4 pi squared is just 1. As well as the mass of the sun and the mass of the Earth, for example, well, the sun is so dominant, and so we just get the mass of the sun. And if I measure my masses in solar masses,